You know, I think that all of us at one time enjoyed learning kinematics and performing all kinds of fun experiments from our little white ivory towers in the kitchen. But as the years go by, a lot of us developed an apathy or even a dread about furthering our understanding of kinematics. So what happened? Now, I know with me, what happened was I got into first year physics class, first semester, and the first chapter was kinematics, and we were introduced to a menu of equations to use, kinematic equations, to solve kinematic problems. And as many problems as I did, I never felt confident that I had a systematic way of finding the right equation or the best equation for solving the problem. And then when test time came around, and later on when the MCAT came around, I was full of a lot of anxiety about whether I was going to be able to get the kinematic problems. They were fun, but they just were very anxiety provoking. So about 5 years ago, when I started reviewing physics tutorial videos online, because I wanted to tutor, came across a guy after a few years that really helped. His name was Stuart Sitter. He's a British teacher. He's had 30 years experience, and his website has some of the best math and science videos I've ever seen. Definitely should check it out. Wonderful teacher. Anyway, he introduced me to the SUVAT method, and things started to click. I really felt like there was beginning a kernel of hope that I might develop some confidence in finally getting kinematic equations. So I worked a lot of kinematic problems by the SUVAT method, and eventually I kind of modified it and added my own little modifications, such as step 3 and 4 here, and I will share that with you. When you get done with this video, you should be able to understand why SUVAT is, in my opinion, effective and a great way to attack kinematic problems. Before I go any further, though, because the first thing I'm going to do is work a kinematic problem for you, the reason I am is because the SUVAT method is sort of like a simplified algorithm when you go through the steps. And when I tried to teach this approach using this diagram here to some of my students, I found that it was sort of abstract to explain. So it's just easier, I found, to just do some problems and watch the steps performed and kind of let it wash over you first, and then go back and analyze why the method really helps direct you to the right equation quickly and effectively. So let's take a look at an overview of what this video is going to cover. This video is geared toward high school students taking physics, college students taking physics, and people that are interested in reviewing for the MCAT, preparing for the MCAT. So we'll work a problem here in a minute. After that, I'm going to take some time to review some kinematic concepts and terms, and I'm not going to jump right into showing you how to do the SUVAT steps and analyzing them in detail until we go through this introductory material. So if you want to fast forward and just figure out how to do the SUVAT problems with the SUVAT method, you can, but I purposely put it down here in the starred yellow further into the video so that we would kind of force you to review some of this material, and also maybe go over some terminology that, in my experience, is confusing for first-year physics students, and hopefully I can help clarify at least working man definitions for some of these physics terms. So we're going to go over terminology, working definitions, mechanics, kinematics, dynamics, statics, do some concrete examples so you really have an understanding of the differences between these terms. Review scalar versus vector. Get an overview of the various types of kinematic problems and how to quickly identify a kinematic problem. And then finally analyze the SUVAT method and why it's effective, and tips on how to memorize the equations. And then if you're interested in pausing the screen and looking at the algebraic derivations and calculus derivations of the SUVAT equations, they're there for you. Finally, I'm going to end with a three-prong approach to mastering kinematics. Some comments also about shortcuts in solving kinematic problems. So let's go back and look at how to do a kinematic problem. The one I'm going to take is from the Khan Academy website. Probably many of you are familiar with Khan Academy's website. It's got a new section for the revised 2015 MCAT, and the Khan Academy people have developed a MCAT test prep section that is excellent. And it also has been reviewed by the AAMC, the people that make the MCAT test, to make sure that the content and the questions that the Khan Academy people have made are pertinent to the test. Alright, so we're going to use these 4 steps, and we'll take this question from Khan Academy, and it says that an ambulance is currently traveling at 15 meters per second and is accelerating with a constant acceleration of 5 meters per second squared. The ambulance is attempting to pass a car which is moving at a constant velocity of 30 meters per second. How far must the ambulance travel until it matches the car's velocity? So what's nice about SUVAT is when you're taking a time test, you really don't have to draw these pictures. I did it here just to kind of orient us very quickly, but you'll find that you'll rely less on having to draw pictures for the kinematic equations. Not that that's not good to get an intuitive understanding, but anyway, so we have this ambulance here, and we have been given that it initially had a velocity of 15 meters per second. It's got a constant velocity. That's important that it's constant, of 5 meters per second squared. And we want to know what the distance it will have to travel, what its displacement will be, which I'm going to use S for displacement, which is one of the letters that is used for displacement in physics. The other is X. Sometimes they use R. We'll use S. And we're interested in knowing how long it will take, how far this ambulance will have to go until it has reached a velocity of 30 meters per second, the same velocity that is of another car's. So let's start with step 1. What we'll do is write SUVAT vertically. That's step 1. S stands for displacement, U stands for initial velocity, V stands for final velocity, A is acceleration, T is time. U comes before V, so U is initial, V is final. Step 2. Enter 3 out of the 5 SUVAT variables next to their letter. So we were given initial velocity, we were given final velocity is what we want, we were given acceleration, and so we enter it next to the letters that correspond to those values. Step 3. Circle the variable that you need. Well, what we need is the distance. We want to know how far must the ambulance travel until it matches the velocity of the car, which is 30 meters per second. So we circle that. That's all we do on the step 3. And then step 4, our final step, is that we draw an arrow through the variable that is left. Well, the variable that's left is time. We draw an arrow through that, and there will be an equation that will be affiliated with the letter T. all of these letters will have equations affiliated with it, which I will get into further down into the video, and we'll get into that. But for right now, if you were doing this problem, you would have known what equation goes with which letter. You would have memorized that, and so you put that there next to the letter. That is the equation that we need to use for this problem. So what we do is we take that equation and we put in all the data that we've been given. We were given final velocity, we were given initial velocity, we were given acceleration, constant acceleration, and we're trying to solve for displacement. Well, we just algebraically solve for s. I'm not going to go through all the math here, but when you do that, you get 67.5 meters. And that's it. Didn't need to draw the picture. Just do the 4 steps. You're done. Okay. So now you've seen it. Some of it doesn't make sense, I'm sure, but it will make perfect sense by the end of the video. Okay. So the first thing I want to do is talk about some terminology. I want to talk about, and this illustration here is very good at summarizing a lot of the terminology. And first thing we want to talk about is, what is mechanics? When you take physics, the first thing you usually study after maybe vectors and some math review is kinematics. And then after that it's usually dynamics and statics. So first of all, let's just talk about what mechanics is. I use a mnemonic to remember what mechanics is. And when we talk about mechanics, we're talking about Newtonian mechanics or classical mechanics. Mechanics is F-E-M, force, energy, and motion. Those are the three things that mechanics is. You can read up here, the general study of the relationship between motion, forces, and energy of an object or a system is called mechanics. So with classic mechanics or Newtonian mechanics, we're talking about objects that can be the size of galaxies all the way down to molecules, atoms, not subatomic, but on a molecular level. In chemistry, you'll learn about the average kinetic energy of gases and the average velocity of gases, of an ideal gas in a container. So mechanics entails the wide spectrum of sizes of objects, and we think of FEM with that. Now, just to distinguish Newtonian mechanics from other types of mechanics, we have also quantum mechanics and relativistic mechanics. Quantum mechanics deals with subatomic particles like electrons and neutrons and protons, and their behavior is a little bit different because they're so small. Because Heisenberg's uncertainty principle says it's the closer you understand the position of an object, the less you know about its velocity. The more you know about the velocity of an object, the less you know about its position. So we're not really dealing with that type of mechanics today. And then there's relativistic mechanics, which is objects that are going very fast, near the speed of light, and things happen, as most of us know, that make it a little bit different, and we have to put into some fudge factors into the equation. So we're not talking about things that go very fast or things that are very small when we talk about mechanics today. Okay, mechanics is subdivided into subdisciplines. I already mentioned there are kinematics, dynamics, and statics. And then there's also the energy portion, which is talk about total mechanical energy of an object, which is the kinetic energy and the potential energy of it. So this whole circle entails different aspects of mechanics. And so when we talk about kinematics, we're really only interested, let's put our little mnemonic up here, force, energy, and motion. We're only interested in the motion of an object, okay? If we're talking about dynamics, we're still interested in the motion of the object, but we're also interested in the forces that act on that object. And when we talk about statics, we're interested in just the forces that are acting on the object in the absence of motion or energy. Okay, so then if we're talking about mechanics, like kinematics, what are we dealing with as far as parameters, as far as measures? We're dealing with the SUVAT. We're dealing with displacement. We're dealing with velocity, initial and final. And we're dealing with acceleration, constant. And you'll be seeing me put constant there a lot, because the SUVAT method, the SUVAT equation, the kinematic equations that you get, even if they're not written in the SUVAT way, are under the assumption that it's a system that's subjected to constant acceleration, and then time. So we're dealing with meters per second with velocity, meters for displacement, meters per second squared for acceleration, and seconds for time. Now you don't have to use these measures. This is the MKS system of measurement, meters, kilogram, second. Most physics courses use that, but you could use another system of measurement. You could use centimeter, gram, second, or British, or a lot of other systems. But as long as you're consistent with the units within the problem, the SUVAT method can still apply. But as far as we're concerned, we're going to be using the MKS throughout this video, and most likely you'll be dealing with that throughout your physics classes. So with kinematics then, if we're not interested in energy, and we're not interested in force, and we're only interested in motion, which is going to be the SUVAT parameters, then a SUVAT problem will not have force or newtons in it. It won't be involved with mass, and it won't be involved with energy, joules. So when you're doing kinematic problem, you shouldn't really be dealing with these measures. When we concern ourselves with the forces that cause the motion of an object, we call it the study of dynamics, as I said. And when we concern ourselves with the forces that cause an object to have no motion, we call that the study of statics. So sometimes you'll see that dynamics is why objects have motion, and kinematics is how objects move. Now when I saw that initially, it made really no sense to me at all. It's just so ambiguous or nebulous. And so what I'd like to do is give you a concrete example of a dynamic problem versus a kinematic problem, and then I'm also going to show you a static problem, because the static problem is really why objects have no motion versus dynamics, which is why objects have motion. So we're going to take a little segue into the future, probably your second chapter that you'll be involved with in physics course that you're taking, and we're going to look at forces here. All right. Oh, jumped ahead. Okay. When you take physics and get into dynamics, you're going to be initially introduced to Newton's three laws, and as the first law states, and we won't read all of it, but if an object's at rest, it will continue at rest unless it's acted upon by a net force. The second law says the net force on an object is equal to the mass of that object times the net acceleration. Most of the time they don't put net in there, they just put F equals ma. And we don't need to concern ourselves with the third law today, but we want to look at the fact that there are lots of different forces that can be imparted on an object. And they can be categorized into two large categories: forces that act at a distance and contact forces. And forces that act at a distance are gravity, electromagnetic, or electrical force, magnetic force. And then there's a series of different types of contact forces: normal force, spring applied, tension, friction, etc. Okay, so let's just go down here and look at a example of a dynamic problem versus a kinematic problem, and really understand why objects have motion versus how objects move. You know, what those two really mean. So let's just pretend like we've got an object here that's 10 kilograms and it's sitting on ice, so there's no friction force. And we're going to have a free body diagram drawn here, and that's what this is. So you'll learn about that if you don't know already. And a free body diagram is typically drawn where the forces radiate out from the object in the x and y direction, and you label them and put the amount of newtons that each force has. So we have this object that's sitting on ice, and we're going to be pulling it with a tension force of a constant tension force of 60 newtons. And it's going to have mass of 10 kilograms, so it has a gravitational force of minus 100 newtons, and minus meaning down. And then it's pushing against the surface, it's contacting a surface, so it will have a normal force of 100 newtons. So if F net is equal to mass times acceleration, well, the vertical forces cancel each other out, and so we're left with a net force of 60 newtons to the right. So when dynamics says why objects have motion, we're interested in the forces that are acting on that object, and we're interested in M, not E, but interested in force and motion. So why does this object have motion? Because it's got a net force of 60 newtons to the right. Okay, so that's the dynamic aspect of this problem. Let's take this information that we have, 60 newtons to the right, and we'll rearrange our F equal ma equation, and we'll put our 60 newtons in, divide by the mass of the object, and we'll find that the acceleration that's on this 10 kilogram object, which is constant because it's a constant tension force, is 6 meters per second squared. So now we have the acceleration. So let's take this exact same problem. This object was initially, we'll say, at rest, and we know now that it has an acceleration that's constant of 6 meters per second squared. We're not interested in the mass. We're not interested in the forces that cause this acceleration. We just want to know about these parameters, the SUVAT. We want to know about displacement, initial velocity, final velocity, acceleration, or time. We want to know how these things are affecting the movement of this object. So let's just take some hypothetical kinematic questions that might go with this problem. So here's this object that's initially at rest, and starting at rest, and it's moving with a constant acceleration of 6 meters per second squared. And we will maybe ask ourselves, what will its displacement be in 4 seconds? So let's use another another SUVAT problem. We'll use this as an opportunity to do it. So the first thing we do, step 1, is we write SUVAT vertically. So we did that. We wrote it vertically. Step 2 is we fill in the information that we have. We need at least 3 data points. Well, we know it started initially at rest, 0 meters per second. We know its acceleration, and we also know the time that we're interested in. The change in time is 4 seconds. What are we looking for? We're looking for the displacement. So we circle that, and then we draw a line through the parameter that's left, which is v, final velocity. Well, the equation that's affiliated with v will be this equation. So now we have our equation that we need. And so we go down and we fill in the data that was given to us in the problem, and we solve for S. And the answer is, in 4 seconds, starting at rest, this object will have been displaced 48 meters. We didn't need to know it's the forces on it. We didn't need to know its mass. We just want to know how it's moving, how this object's moving, and we can predict that based on the information that we have. We could use another opportunity to do a SUVAT here and take exactly the same problem, but just ask a different question about how it moves. Again, starting at rest with a constant acceleration of 6 meters per second squared, we could ask, what will its final velocity be in 4 seconds? So again, we write SUVAT vertically. This time we fill in the information, which is exactly the same information. Step 2. Step 3 now is we're interested in final velocity, so we're going to circle final velocity. And then we draw our line through the equation, or through the parameter S, which is left. And so the equation that's affiliated with S is this equation, and we fill in the information. So we put in A, we fill in T, and we put in U and solve for V. And when we do that, we find that the velocity in 4 seconds will be 24 meters per second. Okay, so let's move on. And we're going to talk about various types of kinematic problems. So you can categorize kinematic problems into 2 large categories: one-dimensional and two-dimensional. One-dimensional is often called translational, which just means straight line motion, one-dimensional motion. Two-dimensional is going to have an X and Y axis to it, so it can be circular motion or projectile motion. So one-dimensional kinematic problems that you typically see in high school courses, first-year college physics courses, are going to be problems where a rocket goes up or down, straight up and down, a ball's dropped. Maybe a ball is thrown off the top of a building, but it's over the edge, so it goes straight up and maybe comes down at the bottom of the building. You could have one-dimensional that's horizontal. Remember, all of these have constant acceleration if they're kinematic problems. At least the ones that we're interested in. You can have kinematic problems where the acceleration is not constant, but that's not something you typically see in the courses that you're taking. So you could have problems of this nature, which don't really need to go into that. You can just see there's different scenarios that you're going to see. Then you could have the two-dimensional problems like the projectile motion. And one of the favorite things the MCAT people like to do is to test you on kinematics, and using the SUVAT method or whatever method you want for the kinematic solution is to use a scenario where you've got maybe 2 electrostatic plates, you've got electric field lines that are going to be the source of a constant acceleration, and you have a charged particle go into this field. And you can apply the SUVAT method to these types of problems. And then the circular problems, we've got things like a blender with maybe a motor that has a constant acceleration to it, or a fan, or maybe a ride at the fair. Again, kinematic circular motions. So what I want to do is make a comment. Since so many problems deal with these type of scenarios that I've drawn here in kinematics, I just want to make some comments about G-force. So first of all, let's look down here at this. You're going to learn, if you haven't already, that the gravitational field lines between two objects, let's say the Earth here, and these little red dots are like maybe a satellite, space station, or whatever, a person even, some object. So the gravitational attraction between the two center of masses of two objects like the Earth and this red dot here is inversely proportional to the square of the distance, which is r. So as you can see, and if you are familiar with this type of mathematical relationship, gravitational force drops off fairly dramatically as the distance between two objects gets larger and larger from each other. So it is pretty dramatic, but when you actually look at do the calculations, let's say a person that's standing on the surface of the Earth, or an object, it doesn't matter what it is, how big it is, and you calculate the gravitational force attractiveness between these two objects, the Earth, the center of mass of the Earth, and the center of mass of that object, and you take that object and you lift it a kilometer above the Earth and calculate the decrement of the gravitational force, it only will drop off about 0.15%. So even about over half a mile up above the Earth, it's not going to drop that much, because the center, well, it's just the relative size of these two objects. So even when you raise an object 400 miles above the Earth, the gravitational attraction only drops off by 10%. So why am I telling you this? Well, because we essentially consider objects, whether they're men or whatever is on the surface of the Earth, and even if it's relatively high above the Earth, is being under essentially a uniform gravitational field. So we don't see this radial distribution of the gravitational field lines. We kind of look at them as equidistant and straight down. And so this picture up here, where I'm drawing these peak gravitational or acceleration vectors for g, acceleration vectors, that's basically what I'm trying to make the point there. G force is 9.8 meters per second squared, which is a, but I always just round it off to minus 10 meters per second squared for simplicity's sake, for calculation's sake, and minus because it's going down, and just by convention, down is, for most people that do physics problem, is negative, up is positive. One more point about the G-force is that it doesn't matter whether you're a little mouse, have the mass of a mouse, or the mass of an elephant. The G-force is the same, because as you look at these two, F over m, remember F equals ma, we rearrange it. F over m is equal to a, but we said that a is equal to g at the surface of the Earth, and even quite a bit above it, and that g is equal to this. So why is g constant if we've got such a big disparity between these two masses? Well, it's because the gravitational force between that mouse and the Earth is less than the gravitational force between this elephant and the Earth. So F goes up when mass goes up proportionately, and F is small as mass is small with the mouse, and so it all is equal to a constant, which is minus 10 meters per second squared. Okay. So, how do you recognize you're dealing with kinematic SUVAT problem? This is sort of a summary now. So one thing is, first thing you do when you look at a problem is you're looking for constant acceleration. Okay, so you've got to have that, and you're looking for it. Sometimes you'll see the problem worded where some object is decelerating at a constant rate. And so you might see this term too. But I do want to make a point about the word deceleration here in a minute. But the other thing you want to do is look for the things that kinematic problems deal with, and that is SUVAT: displacement, velocity, initial and final, and time. So your SUVAT problems, or your kinematic problem, is going to have constant acceleration and the 5 parameters of SUVAT. You're not going to be dealing with newtons. You're not going to be dealing with kilograms or joules. Okay, so if you see that, think dynamics or static problem. Now let's make an important point about the word deceleration and acceleration. When you will see deceleration in word problems, but generally physicists don't like to use the term deceleration. They just use the term acceleration. And let me make a point about that. Here we have an object that's slowing down in 2 scenarios. In the top scenario, we've got an object that is going to the left. It's got a velocity of minus 10 meters per second. Now it's minus because it's going to the left, and I arbitrarily have defined left as negative and right as positive. Velocity is a vector and has direction. So we have to denote that with either a negative positive sign or other means. Generally we use positive and negative. So this is going to the left, but the acceleration of this object is constant and to the right. Now, because the acceleration is to the right, we say it's positive, but that has nothing to do with why this object is slowing down. The reason this object is slowing down is because the velocity of this object and the acceleration on this object are in opposite directions. Now we can take the same situation, it's slowing down, but this time the object is moving to the right, and its acceleration is constant and to the left. So now the acceleration is negative, the velocity is positive, and it's still slowing down. So you can have a positive acceleration or a negative acceleration. It has nothing to do with whether an object is slowing down or not. What has to do with whether an object is slowing down or not is whether the acceleration vector is in the same direction or is in the opposite direction to the velocity vector. So let's look at when it would be speeding up. It could be in this situation where we've got velocity to the right and acceleration to the right. So they're both positive directions. Here we've got, and it's speeding up. Here it's got a negative velocity going to the left and a negative acceleration going to the left, and it's still speeding up. So again, we've got a negative acceleration, a positive acceleration. In both situations, it's speeding up. So in all these situations, we're talking about acceleration. We're not talking about deceleration as an actual physics parameter, although the word is used. Okay. Moving on here. Trying to find my next slide. There we go. Okay. What we want to do now, one more thing before we get into analyzing the SUVAT method, is just talk about vector versus scalar. And I want you to notice that out of the SUVAT parameters, there's only time is a scalar quantity. Displacement, initial final velocity, and acceleration are vectors. So they're going to have magnitude and direction. It's very important to make sure that you respect the direction, which is usually manifest as a positive or negative sign. If you don't, you'll get the wrong answers a lot of the time because you're not putting the right sign into the equation. Okay, these are just some examples of scalar. We're going to specifically look at the difference, a head-to-head comparison between distance versus displacement and speed versus velocity. So let's just take a situation here, a hypothetical situation, like let's say that we have a car. It starts here and it drives, we'll say, 1 kilometer north, and then 2 east, and then 1 north, and 3 east again, and it finally finishes there. So the actual path of this car is the distance. That's what it is, and it would be 7 kilometers. The displacement is only the difference between the start and the finish in the shortest way possible, which is a straight line. So the shortest distance between these 2 points is a straight line, and if we calculate what that value is, we can find out that we've got basically a Pythagorean theorem problem here, and we end up with 5.39 kilometers here. Okay, so we've got distance and displacement, and we can see that they are actually different. Now, if we want to determine the, let's say, the average velocity and the average speed, which is often terms that are used a lot and compared a lot, and questions are asked a lot about the differences between these two in your physics course, let's just assume that this distance, or this trip here that was taken to the finish, took an hour. So that's, since we're using MKS, we're going to convert that hour into seconds. So the average speed definition is total distance, or the actual path, divided by the change in time. So that would be 7,000 meters divided by 3,600 seconds. We find that the average speed is 2 meters per second. The displacement was 5,390 meters. The time was the same, and so 3,600 seconds. And we find that the average velocity, though, was 1.5 meters per second. So one thing that you can say about average speed and average velocity is that the average velocity will always be less than or equal to the average speed. Okay, when would it be the same? Well, let's just say that we instead of taking that circuitous path in this problem here, is that we went straight across, so that the actual path and the displacement are the same. That would be a situation where the calculation for average velocity and average speed would be the same. Okay, so one thing else that's important to mention is that when you talk about instantaneous speed and instantaneous velocity, they are the same as long as you don't add the direction. So why is instantaneous speed and instantaneous velocity the same? It's because when you calculate instantaneous speed or velocity, the distances are so short, they're so minuscule, that the actual path and the displacement are so, there's really no difference in them. So basically velocity is, without its direction, is instant speed. It's not so as important as understanding the difference between average speed and average velocity. So let's take a look at one more typical problem that you might see with average speed versus average velocity. So let's say you've got a circular path, and if you went along the from initially here to here, the arc of this circle or this path would be the distance, but the chord between initial and final, this chord here, would be the displacement. So if you taken that concept a little further, if you had a problem where you were taking a race car around a track, and it went around and ended up back at the starting line, the displacement would be the 2 pi r, the circumference of the track, divided by the time. The displacement would be 0 because the initial and the start are the same. And so in this case, our calculation for average speed would be 2 pi r over delta t, delta meaning the difference of time, change in time, and our average velocity, and that little line over v means average, is just the initial position, or the final position minus the initial position over the change in time, and that would be on top in the numerator a big 0. Okay, it's very important because I mentioned that displacement, velocity, and acceleration are all vectors, that we have respect for the signs. So generally speaking, most people that do physics problems abide by the conventions of the Cartesian axis, Cartesian plot of the x and y axis, where to the right is positive and up is positive, to the left is negative, and down is negative. So typically when you draw your little pictures for your problems, you'll use that convention. The other important thing with signs is to define your 0 point, because of course the interface between a positive and negative zone is going to be the 0 point. Now sometimes it's going to be like in a problem where a rocket goes straight up and comes down, the 0 point will be the ground. But maybe you've got a problem where you've got a rocket hanging over a platform on a building, and you shoot it straight up, and then you pull the platform out and it comes straight down but goes past where the initial platform was and hits the ground. In that situation, you might want to define the 0 point as being the point at which the plank was situated, or the top of this building. So anyway, it's important to keep that in mind. The definitions for average speed we already mentioned. Total distance, or the actual path divided by time. We mentioned this one, that velocity is initial position or final position minus initial position over time. You could just put S for displacement. That's the same thing. Now, average velocity can also be calculated as long as you've got constant acceleration with this equation down here. And that is where you take final velocity plus initial velocity and take the average of them. We'll look at that in a minute as to why that is. And then the average acceleration is just final velocity minus initial velocity over change in time. And we'll look at that here graphically. So let's just take a look at the reason why you can use two different equations to calculate average velocity when you have constant acceleration. Any kinematic object has a triplet of graphs that should always be drawn, or you should be able to draw them. And that is the S versus T, V versus T, and A versus T graphs. So with an acceleration that's constant, it would, let's say a positive acceleration, you would have this horizontal line. Well, when you plot the velocity versus time for such a scenario as this, you're going to get a straight line with a positive slope. So if you take the final and the initial velocities of that line, that would be and you take the midpoint, which is the average distance between these two, that would be one way of calculating the average velocity. The other way is going over to the displacement graph. With constant acceleration, you get a horizontal line, you get a straight positive line. With positive constant acceleration, you get a horizontal line above the x-axis, you get a straight line, and then you get a parabolic curve. So you can take this equation where you take the final and the initial displacement, and you can draw basically a secant line, and that will also give you the average velocity. So if you don't, now this is a situation where you don't have constant acceleration, which is not typically what you see. But if you did have that, then it wouldn't look like that. And so the velocity versus time graph would not be a straight line, so it wouldn't look like that. So the displacement curve might be something, if you had a non-uniform acceleration, a non-constant acceleration, and a non-linear velocity curve, your displacement curve might look kind of crazy all over the place, but you could still calculate the average velocity, again, by taking the final position and subtracting it from the initial and drawing a line like that, and that would give you the average velocity. The average acceleration is actually nothing but change in y over change in x, which is just the definition of a slope. So when you take the slope of a velocity versus time curve, that is the acceleration. Okay. So let's get into the actual kinematics. All right. All right. Why is the SUVAT equation superior? Okay, first of all, we want to look at the problem with the typical way that we see the kinematic equations given to us. They're normally given like that, and often you'll see this next to it where the point is made that in this first equation here, the missing quantity is there's no displacement. Displacement here is final position minus initial position, which is displacement. In the second equation, the missing parameter is initial velocity, v sub naught. In the third equation, the missing parameter that's not in that third equation is final velocity, and then acceleration is not in the fourth one, and time is not in the fifth equation. Okay, that's fine. We're going to still stick to that paradigm with the SUVAT method, but we're going to simplify this. Let's look at why it needs to be simplified. The problem is that one of the problems is that you've got an x and you've got an x sub naught, you've got a v sub naught and a v. You've got two things that have the same letter, and if you forget to put the sub naught in there, and you look at these equations, it can be where you don't know if you've got initial position or final position, or initial velocity or final velocity. That's one thing. The other thing is, notice that when you look at this vertically, it doesn't spell anything. There's no way it spells anything, and that's going to come in handy, and you'll understand why in a couple minutes. But if we change this x minus x naught to displacement s, and we change v sub naught to u, and v we keep the same, just remember that u comes before v alphabetically, so u is initial velocity and v is final. Don't forget to put a tail on that u, so when you're writing your equations that you don't confuse a u with a v. But now we've got something that is going to give us a mnemonic hook. We've got a SUVAT. We've got a word that we can actually say. Now that may not make any sense at this moment, but you'll see why it does in a minute. Okay, so let's look at what's going on with these equations and why we always write SUVAT when is our first step in the SUVAT method. Okay, well, you saw that the missing variable is affiliated with an equation. So we want to be aware of that s is affiliated with this equation, u is affiliated with that equation, and so forth. And as I go through the problems in subsequent videos, I'm going to refer to the first SUVAT equation, the second, the third, fourth, and fifth. So when you memorize them, you'll know what I'm referring to when I say, the second or third equation, etc. All right, now notice that there are 5 variables in SUVAT, or in any kinematic equation there's 5 variables, and that each of these equations only have 4 variables, and that there's always one that's missing that's going to be next to it. Okay, and in any problem you have to have at least 3 out of the 4 variables given to you so that you can find the 4th variable. We have to have only one unknown if we have one equation to solve. Okay, so that's an important observation. Again, I'm going to make more sense out of that in a few minutes. But let's talk about ways that you can memorize these equations quickly. I'll just give you some tips. You really don't need these tips, because if you work through the subsequent problems that I've going to post in the videos, I'm always going to have this next, somewhere on the screen. And so if you just work a lot of SUVAT problems to just convince yourself how much better this method is, which I challenge you to do, you'll eventually just memorize the equations anyway, just by rote memorization. But if you want to quickly memorize them, which a lot of people want to do, one of the things that I noticed is that these equations are two V's are flanking three S's. So it's V, S, 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 V squared. Okay, so that's one way you can set up these equations. And then you'll notice that the first equation is actually just the equation for acceleration algebraically rearranged. So that's the first equation. The second and third equation are very similar to each other. The second equation here has a minus sign in it and has the initial or final velocity in it. The third equation has a plus sign and initial velocity in it. So other than that, they're exactly the same equation. The fourth equation is the average velocity. One way we do average velocity, remember, was final velocity plus initial divided by 2 times time. And then the fifth equation is one that you just will have to rote memorize through brute memory. It's not a hard equation to remember. So that's just one suggestion on how to memorize these, and they'll come faster than you realize. Now again, I'm going to show you the algebraic and the calculus derivations. At least I'm just going to show you the screen work. I'm not going to walk you through every step. But if you're really interested in learning the derivations of these equations, there's a lot of different ways you can derive them, but I'll just show you the two. Okay, so let's go down here and really understand why this SUVAT method is like an algorithm now. And hopefully this will make more sense. All right, so we'll just do another SUVAT problem here. All right, we've got a problem over here that says, discounting air friction, approximately how far will the boulder have fallen in 3 seconds? So step 1, we write SUVAT, which I've already done, S-U-V-A-T. Step 2, well, wait a minute. Before you do anything, take this back. Make sure that this is a problem where the object, this rock, is under constant acceleration. And yeah, it's a free fall problem. A free fall problem is just a problem where there's linear or translational or linear falling of an object. Doesn't always have to be falling. I forgot to mention that. But anyway, this is a constant acceleration due to g-force. So it's got that, and we're asking to find how far the displacement of this rock will be after it drops for 3 seconds. So we write SUVAT. Step 2, we fill in our information. We know that it started from initial velocity of 0 meters per second because we just dropped it out of our hand. It's falling under the influence of g-force, which is minus 10 meters per second square. Watch the sign, and 3 seconds is how far it falls. What do we want to know? We circle it, and then we draw our line through the variable that's left. So let's really understand now, why does that lead us to the equation that we need? Well, because remember, the S is affiliated. When we circle the S, we are saying that this equation that's affiliated with S doesn't have S in it. There's no S in here in this first equation. If you look over at the first equation here, you can see it doesn't have an S in it. So we don't want to use that equation. We circle this. We want that as our answer, but we certainly don't want to use the equation that's affiliated with it because it doesn't have s in it, so we can't solve for s. Why would we draw an arrow to this through v, and that will be, why is that our winner? Well, because remember, v is here is affiliated with an equation that there's no v in it. There's no final velocity in this equation that's next to it. So that's good. We don't have v. We don't have this information. So this is a good equation because this equation contains 4 out of the other 5 variables. It doesn't have v, but it has s, u, t, and a in it. And we have 3 of those data points. Now, again, we notice that we don't have v. So this and this and this do have v in it. So we don't want those equations. When we fill our data points in u and a and t, the equations that are affiliated with those data points have v in it. There's v. Remember, we don't have final velocity. So we fill in u, and it's got that equation affiliated with it's got a v in it. We filled in a over here. That equation that's affiliated with it's got a v in it. And we fill in t. That equation's got a v in it. Well, we don't have v, and we also don't have s. Well, we can't have 2 unknowns. So by filling in the data points, u, a, and t, we're basically saying no, we don't need those equations to utilize for our answer to get s, because we have no v, and each one of those equations have v in it. I hope that makes sense. So this one doesn't have a v in it. The other 3 data points don't have a v in it. The v that's the equation that's affiliated with it doesn't have a v in it, and so it directs us right to it. Now, even if you don't follow that, maybe I didn't explain it very clearly. I definitely don't think I did, and I apologize. But even if you don't understand the actual mechanism by how this 4-step method works, it works. And I highly encourage you to work all these problems that I'm going to give you guys to prove it to yourself how easy this is. Don't even have to think about it. Now, that's not necessarily good that you don't have to draw pictures, but it really will be nice when you're taking the MCAT or when you're doing your homework and you're wanting to get to do something else, or when you're taking a time test in class. Okay, so let's just finish this problem now. So we've got that, we've got this, we've got that. We circled this. This is what we need. We draw an arrow through the variable that's left that we don't have any information on. That directs us to the equation, the only equation of these 5 that doesn't have a v in it. We don't want that. We do need to find s, so let's go down here and look at the math. So we just take that equation that we drew a line to, and we fill in our data points: 0 meters per second, 3 seconds, minus 10, and that's squared, and solve for s. So the answer is that the rock in 3 seconds after you drop it will be displaced minus 45 meters per second. Okay. All right. Now, okay, that right there I will skip. And let's look at, very briefly, now you can stop the video for this, but I do want to show you the algebraic derivations of this. They're actually, it's a good exercise for people that want to review their algebra a little bit. But this is really very straightforward. The problem is it really doesn't, in my opinion, make a lot of sense. It makes sense mathematically, but I'll just show you one of the ways. There's a lot of different ways you can see the derivation of SUVAT, but you can start with this one of the SUVAT equations, the fourth one. I call the fourth one, and start with the definition of acceleration equation, which is acceleration is equal to final velocity minus initial over time. And all we're going to do is we're going to take this equation and we're going to rearrange it 3 times. We're going to well, let me show you the first equation, and maybe it'll make a little more sense. We're going to take this equation here, s equals v plus u over 2 times t, and we're going to substitute for v in one time. We're going to substitute for u in the next situation, and then we're going to substitute in the same equation for t. So where do we get the substitution for those u, v, and t? We're going to get it from the other equation up here. We're going to get it from the acceleration equation. So here we've got a, and we're going to rearrange it and solve for v. And so when we rearrange it, we get v is equal to at plus u, and we're going to substitute for v, and put this in there, which is right here. And then we're just going to clean it up. And you can look at the math yourself. And then down here we do the same thing, but now we're going to solve for u, or substitute for u. So we're going to take the same acceleration equation, solve for u, rearrange it, substitute it, and that's right here. We substitute it, clean it up, and you get another kinematic equation. I didn't mention we got one here. We got another one down here when we substitute for another substitution, and then the last one is we substitute for t. Take the same equation and rearrange for t, substitute it in, go through the cleaning up process. It's a little more tedious for that, but we do finally get to our 5th equation. So all 5 of these equations can be found that way. But really, it's just kind of showing you the mathematics of it. There's graphic ways to show it that make maybe more sense, but this is just the one I used. And then I do want to say this is not geared toward people that are taking calculus, but I do want to say something. If you are taking calculus in college or in high school, and in my opinion, understanding first-year calculus, it's not even that, introductory calculus courses will make your physics equations make more sense. And so, really, the kinematic equations make much more sense, not with the algebraic derivations, but when you take integration or derivation or derivatives or integrals. And let me just show you the way I think it makes the most sense is if you take the remember that kinematic equations are under constant velocity, or acceleration. So we have acceleration is a constant, okay, and then we just integrate that equation, and then when we get that equation integrated, we'll get this equation, then we integrate that, and we'll get that equation. And I'll show you the work here. So if you take this equation, the acceleration, and you integrate it using the definite integrals that you can see here, you'll get the equation after you do the integration for velocity. And then you can take that and integrate that equation and get this. So you can look at the work for those. Then there's one more that complicated that 5th kinematic equation, and you can screenshot this and take a look at this. This one's a little bit less straightforward. There's a little trick step in that. There's plenty of videos to show this stuff, but you're going to see that if you take calculus, that these equations make much more sense from a calculus point of view. Okay, enough said on that. And very important point here toward the end of this video is the three-prong approach to really understanding kinematics. Now, we talked about the SUVAT method, and I'm going to offer you opportunities to look at lots of different kinematic problems and work them, or I will show you how to work them with the SUVAT method to really solidify this and convince you that this is the best way to solve kinematic problems. But if you just mathematically understand kinematic problems using SUVAT, or even if you don't, you're not going to really understand kinematics. To really understand as well as you need to, it will help you. You will certainly learn how objects move by applying these SUVAT equations. But the other thing that you really need to do is understand how to graphically analyze kinematic problems, and then draw pictures too. So that's the three-prong approach. So you can do your SUVAT method, which is really mathematical, and draw a picture with it. That does help. But like I said, I did that with the first problem. But like I said, you don't want to do that when you have a test. But when you're doing your homework and you really want to get a visualization and imagery of what's going on, you just don't want to plug and chug the SUVAT method. That's why I'm a little hesitant about just telling people to fly with that and not understand graphic analysis. I would never dream of that. You really need to apply a lot of time to understanding the graphs of kinematics, and that would be this. Like I said earlier, every kinematic problem tells a story, and every story has a triplet, has 3 stars basically. So you've got 3 actors in the play, and the story always stars acceleration versus time graph, a velocity versus time graph, and a displacement versus time graph. And you want to be able to, you want to get to the point where you can actually look at these graphs and make a story. Now here's 2 stories that I drew that really could apply to these 3 graphs. You want to get to the point where you can do this. If you can't do this, you will not be able to answer half the kinematic questions that will be on a test, because a lot of times they will come as graphs. They won't come as equations where you can apply the SUVAT method. You have to answer the question with graphs, understanding graphs. So I'm going to, after I get done with all the SUVAT series of videos, I'm going to have a whole series of how to read graphs on kinematic problems. And just to kind of give you a sense of what that is, for example, you want to be able to, and this actually is a lot of fun, and it's really easy once you learn the rules. But for example, in this problem, let me scroll this up a little bit more. In this problem right here, you can start with just a V versus T graph and not have the other 2, and draw them. Or you could start with just this graph, this displacement versus time graph, and be able to draw the velocity and the acceleration curve. You can't so much do it from the acceleration curve, but you can start with one graph and figure out the other 2 graphs, as long as it's this one or this one. But for example, in this graph of the V versus T, you want to understand that the slope of this graph is acceleration, and that it's a negative slope, and that means that the acceleration is negative. Here it's -10, and it's constant. Why is it constant? Because the slope of this graph is constant. You also would want to be able to get facile enough that when you see this graph, you know that at this point the object has turned around, and that at this point from here to here, let me clear that a minute, that between here to here, the object's slowing down, and that between here and here, it's speeding up, and that the area under this curve right there is the positive displacement, and the area under this part of the curve is the negative displacement, and that when you add them up, you'll find that this object was not displaced at all. It's right back where it was. Okay, so you can get a lot of information by learning some simple rules, and this is the kind of skills that you need to have to really understand kinematics. You'll understand the difference between velocity and acceleration, which is confusing for a lot of students when they first start out, by learning these how to read these graphs. So as you can see, I said the displacement was 0 because the blue cancels out the red, and you can see that in the displacement picture here. The object started here and ended here. It's right back where it was. Here, down here, you can interpret that as the rocket goes up and comes down. And it says it slows down, and it said it speeded up, and that's what happens here. The rocket goes up. As it's going up, it slows down. It reaches a peak height, and then it falls, and as it falls, it speeds up toward the Earth. And at this point, it turned around, which is right there. You could do this. You could tell the same story using a totally different scenario, like with maybe a rocket with retro rockets on it, or some kind of a car with retro rockets or whatever. But there's other scenarios. Something else you want to get skilled at is when you look at a displacement versus time graph, you want to realize that the tangent at any point, or the slope at any point, the tangent line at any point, is the velocity. So at this point, the slope is 0. That would be right here. Up here, as you can see, initially the slope is very steep. Well, that's right here. That slope initially is 15. It's a slope of 15. And as you can see, as you draw little tangent lines along this displacement curve, it gets less and less steep, and that's as the velocity is going down. And then it becomes 0 here, and then the slope starts to become negative, and it gets steeper and steeper and steeper. And as you can see, the velocity is getting negative, but it's getting higher and higher and higher until finally the slope at this point is just as steep as it was here. It's minus 15. So when a rocket goes up, it leaves at 15 meters per second, turns around and comes back down, its final velocity will be minus 15 meters per second. So this is an example of skills that you want to acquire in reading and graphic analysis. And as you can see, there's a lot of different stories. There's an infinite number of stories. That was just one I just told. And it's often good to put the three graphs, the triplets of graphs, A versus T, V versus T, and S versus T, vertically, so that you can see contemporaneously what's going on at each of the graphs in a more convenient way. You can really get a sense of what's going on with all of these at the same time, and this will really help you understand kinematics when you get practice with this. And here's just examples of different stories. So we could take any of these V versus T graphs and draw S versus T's that go with it, and A versus T's that go with these. And we could do the same with these. We could draw from these S versus T graphs, we could draw V versus T's that go correlate with them, and A versus T. Okay, here's a typical example that came out of the Exam Cracker book, a MCAT question. This is saying, where in this V versus T graph does the object speed up, slow down? So here you can take a look. This is, again, this problem on a MCAT test is one that you could answer in a minute. You don't if you know the rules, you're good to go. So here we've got positive velocity, positive acceleration because it's got a positive slope. So the two are going in the same direction. So this is speeding up here. Here the slope is negative, but the velocity is still positive. It's still in the positive zone. So it's slowing down. So this is slowing down. in this zone 2. Here it turns around, and now the velocity is negative and the acceleration, the slope of this line is negative. So now it's speeding up again. Speeding up. So speeding up, and then here the velocity is still negative, but the slope or the acceleration is positive. So now it's slowing down again. Take you a minute to do that problem once you get familiar with it. And it's going to take practice. So what I'm going to do in these series of videos on graphic analysis is just practice looking at all kinds of different situations. None of them are going to be as complicated as these graphs here. They'll just be simple triplets of kinematic stories. And the best way to tell the story is to just take a ball and show what it's doing. Speeding up, slowing down. You can do it either horizontally or vertically, it doesn't matter. You can tell the story several different ways. Okay. Now the last thing I want to mention is shortcuts. I'm not going to go over shortcuts because the video's definitely gotten long enough, but I do want to acknowledge that at the end, and let me just say this, the reason I'm not mentioning shortcuts is because students want to find these easier, softer ways right away, and they're fine once you get the fundamentals down. But what I have found is that students will learn shortcuts for specific type of kinematic problems, but they really don't have the fundamental tools to solve virtually any kind of kinematic problem. The SUVAT method, if you get really good at it, it can address any kind of kinematic problem. And once you get really good at that, then you can get fancy schmancy and start to learn some of the shortcuts. But I don't want to present those in this video because they discourage students from disciplining themselves, taking some time to work through a lot of SUVAT problems, to memorize those 5 SUVAT equations, and that the letters they are affiliated next to it, to the left of it, and to just apply that. It's really the hardest part is memorizing those equations. Once you do that, this is really a wonderful, easy way. You'll want to, after you do it a while, teach it to somebody. It's a little bit hard to explain, but it's easy to show somebody, and then maybe explain it after you show them how to do a few problems. So eventually we will get to these shortcuts that are, I've got here, but I'm not going to cover that in this video. So thank you so much for staying with me this long. And like I said, in a few days and weeks, in the next ensuing weeks, I'll present some more. Plenty of SUVAT problems to work. All right. Thanks for your time. Bye-bye.